Welcome to qnawire.
Hi, so over here we're going to have to draw the mechanism and the final products of this addition reaction, and we are told that the most reactive double bond will be protonated first. So, so there are two ways to think about this. First of all, in this case, the most reactive double bond will be protonated first. This can be either due to the stability of the reagent or the stability of the transition state. So, in terms of the stability of the reagent, we're going to have the less stable alkene is more reactive, and in the stability of the transition state, in this case, the most stable carbocation would be the most reactive. So, in terms of the stability of the reagent, we are told that the stability of alkenes is going to be the more substituted they are, the most stable that they become. So, in this case, the less stable would correspond to this less substituted alkene compared to the other. Both of them are going to generate tertiary carbocations. So let's examine what would happen. So let's consider the first position, the first attack. I'm going to go with 1 for the first route. In this case, what is going to occur is that, let me draw over here all of our double bonds, is going to be that the attack towards the HCl that we're going to have is going to generate the following carbocation. I'm going to deposit charge here, and now this is going to become a CH3 group. So as you can see, this is going to be a tertiary carbocation that is also going to have a double bond next to it, which are usually called allylic carbocations. In this case, the allylic carbocation is going to be more stable than a standard tertiary carbocation. So even though the second route, the one coming over here, would also generate, let me put it in purple because it's also generates a tertiary carbocation, the reason why this is going to be a little bit more stable is going to be because of the fact that we're going to have a resonance structure contributing to this, in which we're going to have now the carbocation on this position and the double bond over here. So this would be the resonance structures contributing to this addition. Now, just to compare to the second position, let's say that we have the same compound with our double bond over here. But now we are performing the attack over here. So what is going to occur is that we're also going to be able to generate a tertiary carbocation over here that is also going to be an allylic carbocation, by the way. But when we do the resonance structure for this compound, what is going to occur is that now the resonance contribution would be a primary carbocation. Remember that these resonance structures correspond to the movement of electrons over here in this case, towards this position, and in this case, the movement of electrons from here to here. Okay? So, in both scenarios, we're going to have comparable stability of the carbocation, but on the first example, the resonance contributions are going to be more stable. We're going to have a tertiary contribution and a secondary one versus tertiary and primary carbocation. And taking into account also the fact that this is going to be a less stable double bond. This is going to be enough reasoning to consider the first attack to be the main route in this scenario. So finally, the final step would correspond to the addition of Cl- towards this carbocation, generating our final product, which is going to be this one, with our Cl over here. And with that, it would be all. Thank you very much, and have a good one.